As I said before, we're only going to do the front and back of this page today. But this is your informal, or I guess technically this will be your formal definition of your limit. We're just taking the limit of some function as x approaches any particular number. It's going to end up being an actual value. And so the easiest way to find a limit, expand on this, is to use direct substitution. So in example 1, that looks a little crooked, doesn't it? There we go. So in example 1 here, if I plug in 4 into the x value, won't I get a value? And remember, the limit really is, as we approach an x value, the limit is the y value on that graph. So it makes sense that if we use direct substitution, that the limit is the y value as we input an x. And so that's what we're going to do first. So if you can do direct substitution, I always would. And so we're going to input a value of 4. So we get 16 plus 8 minus 5. What value is that? 19. So if we go over to your calculator here, and we input into your calculator this function right here. So go into y equals, and we're going to put in x squared plus 2x minus 5. And then look at the graph. Oh, let's look at the large screen. So look at your graph. So right here, this goes up to what value? Oh, it's the ring of death. Please don't, no. This cannot possibly be good. Maybe it'll only be the TI Inspire that goes. Nope, that's okay. We'll bring that back up. Un momentito. Oh, reopen. Perfect. All right, so let's go back in here and see if it's in there. Oh, of course it's not in there. Try again. So what do I have? X squared plus 2x and then minus 5. All right, so what's the problem with our screen here? What's the problem with the y-axis? What does it go up to? 10. And what is our limit? 19. So I'm going to have to go into my window and adjust my y max. I'm going to adjust it, whoops, went a little too far. I'm going to adjust it to, oh, let's go with 25. And now hit graph. So now as we approach the number 4, so here's 1, 2, 3, 4. So draw, or just look up here at 4, does it appear that we have a y value that's approximately 19? Right? So if I, 1, 2, 3, 4. So if I put a dot right there and went over here, as I approach from the right and as I approach from the left, that has a y value of 19. So the limit does indeed end up being 19. And direct substitution helps us with that and shows that it agrees. At an x value of 4, we do have that y value of 19. So then let's look at part B. Can I use some direct substitution in part B? Yep. So let's go ahead. What can I not plug in for a value for x? Yeah, 1 right here would create an undefined value. So if this were 1, we would not be able to use direct substitution. So fortunately it's not. So the 4 minus 4 cancels, and you're left with negative 5 over negative 3, which reduces to 5/3. So again, we can look at our calculator. We're going to plug in here into y equals. Clear that out. You use parentheses around your numerator and denominator. So parentheses x squared plus 2x minus 5, then divided by x minus 1 in parentheses. And then go to Zoom Standard to get your graph back to, oops, oh, way past it, to get your graph back to where you want it to be. And so it's interesting that this, what's going on here, right here? What do you know is occurring right here? What can x not be? 1. So therefore, don't you see a vertical asymptote here? Now those of you who have the old black brick calculators, isn't it showing like a heartbeat kind of thing here? It looks like a heartbeat. Anybody have the old black brick calculators? Nobody in here. Okay, are you showing a vertical asymptote in here? Yeah. So you just have to get used to ignoring it. All right, so we are approaching what number? We're approaching -2. So over here at -2, here's the y value. Isn't it somewhere between 1 and 2? Right? And then what is this mixed as a mixed number? 1 2/3. So doesn't that seem reasonable? That at -2, go up to your graph at this value right here. If I go over and look at the y value, it's about 1 2/3. Now if we hadn't used direct substitution, would we have guessed 5/3 as the limit? Would we have been able to get 5/3? No, that would have been very difficult. So the graph doesn't always give you an exact answer. So before we do any more examples, let's talk about some properties of limits. So for this first one, all this, oops, you can't see that. How about that? So for this first one, all it's saying is that the limit, and this is a constant, so b is a constant number, as x approaches any number is always that constant. If you think about it, the graph of a constant, like if this were 5, the graph of y equals 5, isn't it just a horizontal line going through the y-axis at 5? And no matter what the x value is, won't the y value always be 5? So no matter what this x value is here that we're approaching, the y value of the function is always that constant. So the limit of the function is that constant. So over here, if we have y equals 14 and we're approaching 5, what's the limit? 14. This one is just also using direct substitution. If I have the limit of x as x approaches any number, we just plug that number in for x and that's your limit. So over here, the limit of x as x approaches 4. We're just going to substitute in 4 for x. Don't we get a value of 4? And remember that function is y equals x. That means every y is exactly equal to every x. So if I'm approaching an x of 4, my y must also be 4. Works the same with powers, and again, I'm just using direct substitution. I'm replacing x with the number that we're approaching, so we get, in this case, c to the n. So in a real number situation, I'm going to replace that x with -2. So I have x cubed, and I'm doing direct substitution in, and I'm cubing that -2. So what value do I get? Yep, so I get a value of -8. Same thing with a power, just using direct substitution. I'm plugging in 27. What's the cube root of 27? 3. So those are going to come in handy later on. Then let's look at operations with limits. So scalar multiplication just means that I'm taking a function. I've given you 2 different functions here, and in these 2 different functions we don't know what the f and the g are, but the limit of the f function is 10. So we don't know what the actual function looks like, but we know that its limit is 10, no matter what value we're putting in there. Well, whatever c is, the limit is 10. And what we're going to end up using these for later is if we have two different functions and we can split an overall function into two different functions, we can use these properties to help ease our finding of the overall limit. And so I'm going to also let, I'm going to let the g function be green. Okay, so the first one says that if I'm taking any function and multiplying it by a constant b, just take the limit, so find the limit of that function and multiply it by that constant. So if I had 6 times f of x, find the limit of your function f of x, which we know up here is 10, and just multiply it by 6. So I end up with 6 times 10, which is 60. We can add and subtract functions. So if you can split an overall function into two different functions that you're adding or subtracting, find the limit of those two functions separately and add or subtract them. So here I've got the f function plus the g function. So I'm just going to add their limits together. So we end up with, I'm going to move this over a smidge. We end up with 10 plus 5. Which gives us a total of 50. Same thing with multiplying. I can multiply the two functions together. So I can take the 10 and the 5, which are the limits of those functions, and multiply them. So I get 50. Or division. I can find the limit of the numerator, find the limit of the denominator, and then divide those. So in this case, the limit of the numerator is 10, the denominator is 5, and we get an answer of 2. And then same thing with a power. If I have something raised to a power like 2x minus 3y raised to the third power, if I find the limit of the 2x minus 3y, and then I can raise that to the third power. So my limit for the f function is 10, and I'm going to square it, and I get 100. So we're going to use more of those next week when we go through parts 2 and 3. So any questions on those? All right, so let's actually get into the meat of things and look at the back of this page. All right, so example 2, we're going to find limits with tables. So I'm going to expand this pretty big. Okay, so on this one, can I use direct substitution to find the limit? What's wrong? It creates a 0 in the denominator. You can't divide by 0. So some of your homework questions ask you that, and you have to be able to say, you can't just say it's not possible. You have to be able to explain why. Division by 0 is not possible. So those are the kinds of things I want to hear. And so since direct substitution doesn't work, then we're going to use, as one of our tools, a table of values. So we're going to come up with an x value and a y sub 1 because we're using it off of our calculator. And we are approaching 1. So I want to get a value that's to the left of 1, but really, really close. I also want to include 1, and then I want to get values that are to the right of 1. I want 7 values total. That's what you're going to have. And then remember, so 1's going to be right here in the middle of our table. You've got to go from smallest to largest. You can't just throw in numbers wherever you want to. I want them going from smallest to largest. And so what number is really close to 1, but to the left of it? Smaller. 0.9. So I want to go out to 2 decimal places. So let's use something like 0.97. There's 1. 0.98 and 0.99. Aren't I getting closer and closer to 1, but I didn't hit 1? Right? Then in the middle, I want you to put 1. So I'm going to put 1.00, and then what's a number that's bigger than 1 but really, really close? 1.01, 1.02, and 1.03. Then we're going to go over to our calculator, and we're going to, I'm going to move this over so I can actually see it. There we go. So we're going to go over to our calculator, and we're going to put into y equals clear that out, our actual function that we have. So use your parentheses around your numerator and denominator. So we've got x cubed, so use your caret. And with the newer calculators, you have to scroll to the right to get out of the exponent. And then minus x squared. And then plus x minus 1. And then divided by x minus 1. All right, so check your table set. So you're going to go into not the window, but you're going to do second window. So second window, check your table set. If the independent variable says auto like this does, you want to make sure it says ask. So I'm going to scroll down and to the right. I'm going to light up ask. I have to hit enter for the auto to go away. So make sure that yours looks just like that. And then when I do second graph to get to my table, I have either blank values or you might have some previous values that you put in there. We're going to plug these values in right now. So we're going to do 0.99, 0.98, 0.97, and then 1. We expected to get an error at 1 because we know that there's a vertical asymptote there. And then 1.01, 1.02, and 1.03. Okay, so you're going to record those here as part of your work. So I'll just quickly record them here. So 9.8. Oh, I went backwards. Oh, see, look what I did. Okay, so since this is going to bother me, I'm going to go fix it. I want that to be 0.97. I did exactly what I told you not to do. There we go. So what do you notice as you go from top down? What's happening from the numbers from top down? They getting bigger or smaller? You can always ignore the numbers that are the same. Look at just the 409, 604, 801. Bigger or smaller? They're getting bigger. And they're getting bigger and approaching what number?
2.
2, right? Because 1.98 is really close to 2. Then we hit 1 and we get an error, of course. And then here, go from the bottom up. 609, 404, 201. What are these numbers doing? They're getting smaller. And they're getting smaller and they're finally approaching 2. So let's look at the graph. What do you think the limit is? 2, because that's what the graph is, or that's what the table of values over here is showing you, is that as we get closer and closer to 1, the y value is getting closer and closer to 2. And so as we approach 1, so here's 1, go up to your graph right there. What does the y value appear to be? 2. So as I approach the 1 from the right, I start on the graph up here and I get closer and closer to 1. My y value gets closer and closer to 2. As I approach 1 here from the left, on the graph I get closer and closer and closer down. Finally I swing back up until I hit a y value of 2. Technically on your graph, and your calculator won't show it, shouldn't there be a hole right here on your graph? But remember, your calculator won't show that. All right, so any questions on that one? All right, so let's look at the next one. Move this over. So this next one, in fact, maybe I'll just move it over here. All right, so on this one, couldn't we use direct substitution and just plug 4 into that? Move that down a little bit. Couldn't I plug 4 in here? Is there any reason why I couldn't plug 4 in here and evaluate it, have an actual answer? All right, but we're still going to use our table of values. So our x value versus our y. Oh, we forgot to put our limit in on the other one, so we'll write that in when we're done. So remember, we're approaching 4. So we're approaching 4 here. What number is really, really, really close to 4, but is to the left? 3.97, right? So that's where we're going to start. And then 3.98, 3.99, and 4.0. And we're going to get bigger. 4.01, 4.02, and 4.03. And we do expect an answer this time for 4. And so I'm going to move this way over. And we're going to go here to y equals and put in our new value. So you do have to use parentheses around the 1/2. And so when you go to your table, you have all those old values in your table that we put in before. So you're just going to write over those. Ben, you can join in. So write down the values as I put them up there, right? Whew, it takes a long time to type on the computer. Okay, so here are your values. Okay, so as we go from top down, what do you notice about the numbers? 405, 602, 801. They're getting bigger and they're approaching 3, right? We actually have a direct substitution value for 4, which is 3. And then these ones, over here we've got 605, 402, 201. So it's getting bigger, starting at bigger and getting smaller, and it also is approaching 3. So the limit appears to be what? 3. And let's just double check the graph. So let's look at the graph. So we're approaching 4. And so here's 1, 2, 3, 4. And as I go up to the graph, what's the y value at 4? 3. This graph has no hole in it because there's no undefined values. So this graph is a parabola. And so that matches. So let's go ahead and write over here what our limit is. And since we'll go back and write the limit on the other one as well. So the limit as x approaches 4 was equal to 3 on this one. And then let's, oh, you can't see that. Let's move this over. All right, so let's go back to this one and write in our limit there as well. So the limit as x approached 1 was what value? It was 2. All right, so let's do the last one with tables, which is C. Let's move this back over. Okay, So for this one, we're going to plug in to y equals our new function, which is x minus 3, use parentheses, divided by x squared, whoops, parentheses, minus 9. So go to second table, and we have our old values in there. But let's go over here and set up our table of values. So what's really close to 3, but smaller than 3? 2.97. And so we're going to plug those values in here. And as expected, we got an error message. All right, then we'll record those. This one's a little different, and it's a little harder to read the limit by the table. And again, we expect an error because if you plug in 3 or negative 3 into the original function, it's undefined. So this is a perfect example of a question where if I'm using a table of values, I like to look at the graph as well. The graph is going to tell us a lot of pieces of information. It appears that as I get closer and closer to 3, what's happening to the y value here? Look at this as 750, 722, 694. It's getting smaller. And what do you think it's approaching? It's either approaching 1.6 or it could be approaching 0. But here's the problem here. This one, normally it goes from big to small, but this one's going from small to big. It's like, why? What's going on? So that's why I like to look at the graph. So look at your graph. Here's a vertical asymptote at x equals negative 3, which makes sense because negative 3 doesn't work here, but there should be here at 1, 2, 3, it looks like it's approaching what? 0. And it's actually touching the x-axis. That's the way the calculator is showing it to you. It's really not touching the x-axis. But at 3 here, there should be a hole in the graph. Let's zoom in and see what's really going on. So we're going to zoom in and hit enter. And then because we're approaching 3, I want to change my window to where the x value max is, let's just say 5. And now look at your graph. So is it touching 0? No, but it is getting really, really close. So here's what's happening, and here's why you see these values here going from small to big, because here's 3 right here. As we approach from the right, isn't the y value getting bigger as we approach from the right? True or false? Yes. And as we approach from the left, isn't the y value going down as we approach this value of 3? But overall, this number is getting really, really close to what? 0. And the reason why I say 0 is it's handy for you to know your exponent rules, or I'm sorry, your horizontal asymptote rules. So if I were you, I would write your review of your horizontal asymptote rules up here. It uses the degree of your numerators, right? So look at the degree of our numerator here. What's the degree of the numerator here? This is the highest degree term. What's its degree? 1. No. Well, the x is 1, right? So the degree of the numerator here is 1. I'm going to put that in blue. And what's the degree of the denominator? It is 2. Isn't this less than right here? Whoops, that's a terrible less than sign. Isn't the numerator degree less than the denominator degree? So, little aside here, when your numerator equals the denominator, you get your horizontal asymptote is the ratio of leading coefficients So if this had been x squared minus 3 here over x squared minus 9, then we would have taken 1 over 1, and you would have seen a horizontal asymptote of y equals 1, and then we would have been approaching 1. Well, that didn't happen here. Instead, we had the numerator was less than the denominator. And so in this case, we get y equals 0. And so that's why our limit is 0. That's why we're approaching 0. And then finally, if you have the numerator greater than the denominator, then you have no horizontal asymptote. And so for our purposes, we have y equals 0 as our horizontal asymptote. And so that's how we know that our limit as x approaches 3 is equal to 0. So that's a harder limit to see, but we're now bringing in our knowledge of horizontal asymptotes. Yes?
Is the first one n equals d? Or
that's
what?
an equals. Yeah, so let's make that quite clear. Equal, whoops. Is that better? That's the equals.
Yeah.
It makes me look like I have kindergarten handwriting with the stylus. All right, so that was, it's not always easy to use a table of values. So if I were you, I always look at the graph when I'm doing table of values. But this is the work that you need to show when the question says use a table of values. So show your table of values. I also like to use the graph. So I typically will not ever just use a table of values. I'll always double check it with a graph or even direct substitution if at all possible, because that's always the most exact. Yes?
Can you tell me what I meant to do on that? Like the numerator.
This you're just writing for your notes. That you're writing for your notes. This is what I would expect to see, and then because this is it's kind of a weird situation, and then when you look at the graph over here, it's like, okay, now I understand why the values here were, starting small and going big, because coming from the right, I do go small and I increase, right? Whereas from the left, I start big and I go down, but right here at 3, it is starting to approach 0. Yes?
Where did you get the 1?
To find your degrees of your numerators, whoops, let me get this back to where you can see it. Take your degree, so which of these two terms? Okay, it's getting a little slow on me, hang on. There we go. Out of the x and the -3, which is going to have the highest degree? The x, and it has a degree of 1. It has an exponent of 1. In the numerator, the x has an exponent of 1, right? That's where that 1 comes from. And in the denominator, the x squared has the highest degree, doesn't it? And so that's where the 2 came from. So always take the degree of the highest term. Okay? Any other questions on that? Can we move on? All right, so let's look at example 3. So now we're going to find limits from a graph, which I always like because it's a little bit easier. So we're going to take and put this function into a graph. It's linear. And so we're going to go over here into our calculator and hit zoom standard so that you get back to your normal viewing window. And then you can put in your y equals. So we're putting in 2 minus x and we're going to look at the graph. So you want to pay attention to where it's crossing the x and the y axis, because that's what I'm going to be checking. I wish I could put a straight line on here, but I can't, so I'll do my best. So that's the graph of y equals, whoops, there it is. That's my graph of y equals negative x plus 2, but we're going to use the calculator one because it's so much prettier. So what number are we approaching? You might want to over here circle this number, because that's where you have to focus. We are approaching an x value of 3. So look back on this graph. Here's your x value of 3. What's the y value at 3? What does it appear to be? Negative 1. So as I approach from the left, the graph, the value of y gets smaller and smaller and smaller until at 3 it approaches negative 1. From the right, it gets bigger and bigger and bigger until it approaches negative 1. And if I use direct substitution, what's 2 minus 3? Negative 1. So I like to always put a circle on my graph where I'm approaching. And so this is 3. And then this is the place on my graph where I'm approaching. And from the right and from the left, they both hit that same y value. And that y value is indeed negative 1. And I've just double checked with direct substitution because I like direct substitution so much more. You can't always get an exact value on your graph, or your table for that matter. So I always like to double check with something else. Does that make sense? I'm just looking for a y value at that x value. So then look at the next one here. So we're going to go into our calculator and we're going to plug in. You're going to do this one this time, so you do this one on your own. So I'm going to cover up your viewing. Those of you at home can see what I'm doing. So work with me. Make sure that when you plot it, you plot where the graph crosses the x and the y axis. So tell somebody what you think the limit is. And use a second method to verify what you think it is. So what do we think the limit is? I'm going to look at the pretty graph. So I am approaching 2. So as I go up onto this graph at 2, what does the value of y appear to be? At 2, what's the value of y? Come on, this is an easy one. 1. And if I use direct substitution, if I plug 2 into here, what's 3 minus 2? 1. So at 2, I like to put a circle on my graph. So as I approach the value of 2 on the graph from the right and from the left, it does have a limit of 1. The y value is indeed 1. You okay with that? The next one's a little bit harder to wrap your brain around. So we're going to use some previous knowledge as well. So let's go ahead and move over and look at C. So let's start by graphing in the calculator first. So go to y equals, clear that out, and you're going to put in sign of pi, so second caret, then x, divided by 2, and then end those parentheses. Check your mode. on your calculator and make sure that you are in radian measure. If you're in degrees, the graph is not going to look correct. So double check your mode, make sure you're in radians, and then you can hit graph, and you get a pretty little sine curve, don't you? Isn't that fun? But I would like to zoom in and look at that a little closer before I graph that. So I'm going to zoom in, and I like that much better. So let's recall the unit circle. So this is 0 on the unit circle. This is positive, this is negative. So 0 on the unit circle, what's my first tick on the unit circle? Well, we're going positively. So unit circle, let's go over here and draw the unit circle. Well, let's go ahead and put in this first. Yeah, it is pi over 2. Write yourself a note that your calc, put calc in radian mode. And then we have 1, 2, 1, 2, 1, and 1. So on our unit circle, this is 0. What's this tick right up here? Pi over 2. Then this is pi. So that means that right here, this is pi over 2, and this is pi. But as we go left and negative, what's this one going to be? Negative pi over 2. So that comes into play from here, going that direction, right? So that means that this is negative pi over 2, not 3 pi over 2. It is 3 pi over 2, but we're going to view it as negative pi over 2. So then I want to look at the ordered pairs that are there. So at 0, what's the ordered pair? Is it 0, 1 or 1, 0? It's 1, 0. And then this is 0, 1. And this is negative 1, 0. And this is 0, negative 1. Oh, and then let's label this negative pi over 2 and negative pi. And then this is positive 1 and negative 1. Well, oops. Okay, well, I'm not going to erase that now. Too late. All right, so based upon our graph, I'm going to go ahead and graph that sine curve, and then we'll talk about it. So it starts at 0, goes up at pi over 2, down at pi. Down at pi over 2, and back up at negative pi. So there's our pretty little sine curve. Now the problem is that we are approaching negative 1. Do you see a negative 1 here on the x-axis at all? No. So it's going to be kind of hard to approach negative 1 on the x-axis. So instead, can I use direct substitution in here? Yes or no? Yes, and so we are really approaching, if I substitute in negative 1 in here for x, what's negative 1 times pi over 2? Negative pi over 2. So we are actually approaching negative pi over 2 right here. So as x approaches negative pi over 2 from the right and from the left, here's the value on the graph. So what y value is that? What's the range of sine? Negative 1 to 1, right? So isn't that negative 1? Well, look at your unit circle. Where is there a value of negative 1 on the unit circle for sine? And sine, which is sine, the first or the second? The second, because it goes alphabetically. So like on this one down here at negative pi over 2, see how sine is negative 1 here? And see how we have a y value here of negative 1? So as we approach negative pi over 2, because we plugged in the negative 1 in here to see what this was, because technically we're plugging into the sine function, negative pi over 2, so that's what we're approaching, because that's where we're finding the value of sine. And then the y value at negative pi over 2 is negative 1. And therefore our limit is what? Negative 1. So the trick's going to be a little bit harder for you. But that was a beautiful explanation, if I do say so myself. Always review it again. All right, so let's look at the last one, which is D. This is an absolute value, which is interesting. So let's go ahead and put that in our graph. So go to y equals and clear that out. And then where do you find your absolute value? Where do you go to put in absolute value? The math button. So go to your math button, and then from there, where do I go? Go over to number, and you see this abs. If you have the old calculator, when you hit enter here, it's going to actually say ABS with beginning parentheses. So you just have to put in our case, x plus 2. And then make sure you end those parentheses if you have the old black brick TI calculator. Other than that, you're going to scroll out of those absolute values and hit divided by, and then parentheses, x plus 2. These are kind of fun graphs. So if I graph it, look at our graph. Oh, we want to go back to our standard viewing window, although that's not so bad. But I want to go to Zoom Standard. Uh-oh. Let's go back to Zoom Standard. Oh, no. Let me guess. It's going to poop out on me again. Y equals? Terrific. I love it when technology doesn't work. Okie doke. Well, while it gets to thinking, let's go ahead and graph it over here. All right, so we've got our it'd be helpful if I had it on graphing. All right, so according to our calculator before it pooped out on us, what is happening here? And we're approaching -2. So what's the height up here? 1, and what's the height down here? -1. And your calculator's not going to show it, but aren't there going to be circles, open circles here and open circle there? Because can x have a value of -2? Can x have a value of -2? Nope. So there should be a vertical asymptote going through there, and so you're going to create one. So at -2, I have an open circle here, and my graph is going to the right. And at -2, I have an open circle down here and an arrow going to the left. So this one's interesting. As I approach the graph from the right, as I approach -2 from the right, so we're going to record this one, as x approaches -2, and we're going to put an elevated or an elevated plus, meaning that I'm approaching -2 from the right, so that plus that looks like an exponent means I'm approaching from the right. What is my limit? What's the y value? 1. But as I approach -2 from the left, so as x approaches -2 from the left side, what is my limit now? -1. Does the left and right limits, do they agree? Yes or no? No. And so write yourself a note. These must agree. And they don't. So therefore, hold that thought, the limit, what does the mean girl say? The limit does not exist. The left and right hand has to agree. So as you approach from the left and from the right, you have two different y values right here at -2. You have a y value of 1 and a y value of -1. And so because they don't agree, the limit does not exist. Question? Okay. Now that doesn't mean to say that the limit doesn't exist anywhere else. So let's say that we changed, instead of approaching x equals -2, let's just say that we approached 2. As I approach 2 from the right, what's my y value? 1. As I approach 2 from the left, what's my y value? 1. So the limit does exist as x approaches 2. The limit as x approaches 2 is positive 1. What would be the limit as x approaches negative 3? So as I approach negative 3 from the right, I am going 1, and then all of a sudden, boop, I go down to here and I approach it at negative 1. And I approach negative 3 from the left, now all of a sudden, negative 1. So the limit does exist everywhere on that graph except at negative 2. Mostly because there's a vertical asymptote there. Well, it's not always because it's a vertical asymptote. It's because it's the nature of that particular equation. All right, any issues, problems, or concerns with that? All right, so let's go ahead and look at limits that fail to exist elsewhere, since we've talked a little bit about it here. So I'm guessing my calculator is no longer going to be good, so
Just exit out of it.
well, I tried that, it didn't want to. Oh, there we go, so we're going to quit. Maybe it doesn't want to. We'll give it time. All right, so go ahead and put this in your calculator, and I want you to draw the graph and figure out what that looks like. So we just did one just like it, so you ought to be able to do this. Put in your calculator. So apparently, it doesn't even want to quit SmartView. I guess we're done with that for today. But this is what it looks like if you plug it into your calculator. And so since we are approaching 0, what is the limit as x approaches 0 from the right side? So as we approach from the right, what's the value of y? Huh? What's the value of y? Yeah, isn't it 1? As we approach from the right, isn't it a y value of 1? So the limit from the right is 1. As we approach 0 from the left, so as x approaches 0 from the left, what's the limit this time? Negative 1. So again, you see the left and right hand limits not agreeing. And so write yourself a note that you want to always be comparing. So compare right and left behavior. And so this limit, overall limit, DNE, does not exist. All right, can I move that? So it was just like the last one, right? All right, so then look at B. I feel like that's crooked. There we go. That makes me feel better. So you go ahead and graph B. Put in your calculator. Obviously, I can't put it in mine anymore. What can x not be? 0. So we're going to have a vertical asymptote going through the x-axis at 0. And then look at your horizontal asymptote. So let's go back to our rules. What is the degree of the numerator? 0. What's the degree of the denominator? 2. 0 is less than 2. Numerator is less than denominator. Is there a horizontal asymptote? Yes. What is it? Y equals 0. So that means the x-axis is also acting as an asymptote. So it's not surprising when you see the graph looks like this. So let's look at our limits. As we approach 0 from the right, what is happening to this y value? It's getting larger and larger and larger. So here's how we write that. As x approaches 0 from the right, so that upper plus means from the right, it is actually, when a number gets bigger and bigger and bigger, what do we call that? Infinity. So it actually is approaching infinity. It's increasing without bound, okay? And then as we approach 0 from the left, sorry about that, what's happening? So it is also increasing, approaching positive infinity, right? So as x approaches 0 from the left, it also approaches positive infinity. So you might be led to believe that the limit is positive infinity. Not so. A limit by nature is a limit. Is there a limit to infinity? No. So both the left and the right are increasing without bounds, so therefore the limit does not exist. And so we're going to write that. Does not exist. But bless you. Your reasoning below, as x approaches zero from either the left or right, f of x, which is your function, increases without bound. So that's going to be something you get used to hearing. It's this notion of increases without bound. So it's not always left hand. I mean, here we have an example of where the left hand and the right hand do technically agree, but it's not a true limit. All right, can I move that? Oh, apparently not with that. So hold that thought. Forget how I group those. Arrange. Take it out and maybe I'll group it now. Great, now I'm locked in here. Where are they? Darn that thing. One more time, and then I give up. Seriously. Let's try this now. Okay, well, whatever. I'm going to take it away because it's starting to irritate me. So let's move. Seriously. Again, I hate technology. Yeah? No. Am I teaching? Am I trying? Am I trying to teach? No? So therefore you're still learning. Okay. Hold that thought. Arg. There we go. Oh, life is good again, but nothing else is moving with it. All right, so here we go. All right, so plot that into your calculator. What do you get? I really wish that I could have my calculator showing up here, but it's not going to participate. I don't want to see that cell phone out one more time. That's like the third time you've had it out. All right, so that's still not cooperating. All right, so if you graph this in your calculator, go ahead and put that in your calculator. What do you get? Make sure your calc is in radian mode. Don't you get something funny that looks funny right around here? It looks like a little blip, right? It goes in from here, it's got a little blip, and in from here. Zoom in on it. Zoom in twice on it. So number one, you want to put calc in radian mode. And then you want to zoom in twice. You're going to get something that looks like the following. So if I had, there'd be like, let's see, if I zoomed in, there's 1 and -1. So it goes down at -1 and it goes up at 1. But then it does this really fun party in the middle, doesn't it? If you zoom in on your calc. So if you don't have your calculator with you, because I obviously can't show you here today because the TI Smart View is not working, I want you to try that at home to see if you can get that. So as I approach, and we're approaching 0, so as I approach 0 from the right, what's happening to the y value? It's going up and down and up and down and up and down. And from the left, what's happening to the y value? It's going up and down and up and down and up and down. So this is called oscillating behavior. So oscillating behavior as x approaches 0. So that means that the limit does not exist. So that's another way for a limit to fail to exist. Then look at the last part here. This will go pretty quickly because we're going to use our algebra this time. So if we use our algebra, I still can't on question A, I still cannot use, Todd, when I'm done, I still can't use direct substitution. Why? Why can I use direct substitution here? Yeah, you get 0 in the denominator. So instead, and we did a little bit of this when we did derivatives, if I take the limit as x approaches 1, can't I factor, and you might not remember how to factor a cube, difference of cubes. I shouldn't see any heads down. Take the cube root of the x cubed, take the cube root of the 1. What do you get? What's the cube root of x cubed? X. Cube root of 1? 1. So you get x minus 1. And then for your next parentheses, take the x and square it. Then multiply these two together. So I get x times 1 is x, and it's a plus. And then square this. 1 squared is 1. So that's your fast review on factoring cubes. And then magic happens. Why magic? These cancel. And so you're left with the limits as x approaches 1 of x squared plus x plus 1. Now can't I use direct substitution? And that's what we're going to do. So I get to put a 1 in. So I get 1 plus 1 plus 1, which is 3. And if you looked at the graph, you would discover that it's a graph of a parabola because the x minus 1's cancel and you're left with a quadratic. And there's a hole in the graph at 1, but where that hole is, it would have been a y value of 3. So look at the second one. Yeah.
How'd you get x squared plus x plus 1?
So we took, what did I just do? Wrong thing. So I took the cube root, first of all, each of those, right? So the cube root of this, cube root of that, that's what went here. Same sign, same sign. When this is a minus, these are both going to be positive. So then I took the x and I squared it to get this. Then to get the middle term, take this term times this term. So x times 1, that's where the x came from. And then to get the last term, square this. So I squared that and got 1. Okay? So if there's an 8 there, if that was an 8, we would have had a 2 here. This would have ended up being a 2x there, and that would have been a 4. Okay? All right, then look at B. You go ahead and factor these two on your own. Factor both of those on your own. I'm going to cover up for you, but at home they'll be able to see what I'm doing. So you factor and you find the limits. None of these could we have used direct substitution initially. When you get values, I want you to share those with people around you. So share your limits with those around you. Talk about them. Check out, put the equations in your calculator and check to see the limit that you came up with. Does that appear to be correct on the graph? Talk. Nobody's talking. Talk, talk, talk. Let's go. It's not a choice. Talk.
You got it.
Yeah, we already talked. We said 2. We said 2, and then we're like, good.
Yeah, but there's more. You got to do the second one too. You're doing C also. No wonder you've done so quickly. You're doing both of them. All right, are we good? What did we get for B? A limit. 2, and for C? Easy, right? There they are. And if you check those with your graphs, they do check out, literally.